Hello, my name is Raul Longoria. I'm the professor for this course, the Dynamic Systems and Controls Lab. I'm going to give an overview of the Dynamic Systems and Controls Laboratory. The course aims to demonstrate and reinforce the kinds of principles and methods that you'll be covering in a related Dynamic Systems and Controls course that's taught here in the Mechanical Engineering Department at the University of Texas at Austin. We meet in the lab for 2 hours, which means we keep the experiments relatively simple, yet focused on practical application of the types of systems that you will be not only studying in lecture that might be applicable to real applications, but also the use of measurement instruments and sensors and actuators. We like also to give you opportunities to learn how to use these tools independently. We also try to have you experiment with designing experiments, and sometimes that means understanding the system well enough, and that might come through the process of modeling the system in the way that you'll learn how to model them in the ME344 lecture. So in summary, the course really wants to provide hands-on experience in building models. That includes developing digital simulations of the types of models that you will be learning how to build, not only in this course but also in the related lecture course, design experiments, and also an emphasis on computer-based measurement hardware, software, and this includes their use in implementing control systems with feedback. The topics that are covered in a DSC course relate to modeling, analysis, and control of engineering systems, and in the way this is taught here at UT Austin is we like to cover mechanical, electrical fluid, and sometimes thermal systems, as well as electromechanical devices, different types of machines. We emphasize deriving mathematical models. This includes, as we'll explain, either linear and nonlinear first, second order systems, and how to derive equations also in a state space form. In addition, the derivation and use of transfer functions for understanding the response of systems and their characterization using those types of relationships. You focus also on analysis of those models to determine the response, both in the time and frequency response, either with or without forcing, which means input forcing. And also the course introduces methods, basic concepts in feedback control. So these are all topics that we try to touch on in the DSC laboratory as well. Now, what do we mean by a mathematical model? Well, in this course and in the 344 lecture, we use algebraic relations, obviously, usually to understand basic component models. These could be linear or nonlinear functions of this form. We also derive first and second order ordinary differential equations for some of the simpler systems, and note these could be linear or nonlinear. We introduce you to the use of what we call state space equations, and this is basically a description of the differential equations, not in nth order differential equation form, but in as a system of first order ordinary differential equations. And since we're focusing on ordinary differential equations, that means that we make simplifying assumptions so that we model the systems at a higher level, and I'll say something about this shortly. And of course, we introduce the use of mathematical models in the form of transfer functions, which are representations primarily for linear systems that relate inputs and outputs of interest in a system. As engineers, we're interested in how systems vary dynamically. So when we study dynamic systems, this implies, right, that we're interested in how maybe one or more independent variables, and these are dynamic variables in a system, vary over time, right? So in general, an engineering system might have some function that relates, variables such as x. Let's say let x be an independent variable, could be space or time, and then there's some variables y and higher order derivatives of y, say, and there's also some variables u that might be inputs to the system. So in general, these could be partial derivatives of the variables y, which represent physical variables of a system, with respect to those independent variables. So you could have multiple variables. This represents a very complex representation where you might lead to partial differential equations. In the dynamic systems course, we're primarily interested in system level models, making lumped parameter representations of systems models. So we always focus on ordinary differential equations and how the variables that are described with time as a single independent variable. So we might have this function reduced so that time is our independent variable. We're interested in y as a state and maybe derivatives of y or other dynamic variables. And then we might have some inputs also to the system. So we're primarily interested in representations of the system as ordinary differential equations. As an example, a first order linear system would take this form, as you might recall from previous courses. You have x here is the state of interest, could be represent displacement, it could represent temperature, and you might have tau as a system parameter that represents, say, a time constant. And this equation, being a first order derivative, would be what we call a first order system, and u would be some input. So this is a standard first order differential equation. And we like to study these forms because they can be used to represent many types of systems. So for example, that same form could be said to represent a system of this form where you have a mechanical damper and spring, and it could represent, for example, the dynamic displacement, the dynamics of the displacement of that spring, or say the charge on that capacitor. These are the types of systems that you will be studying in your ME 344 class and learning how to derive these kinds of differential equations for those types of systems using physical laws and basic representations of the elements in that system. And now we've been talking about linear and nonlinear systems, and how is that important? Why is it relevant? Well, to begin with, the linear and nonlinear relationships commonly arise in what we call the constitutive relationships for the system elements. So a system element, for example, in a mechanical system might be a simple ideal spring, and how that spring force, say, is related to the displacement of that spring could be represented by a simple Hooke's law type relationship where the force is related to displacement, right, through some stiffness K. This is a linear relationship, right, X here being either the extension or compression. If you have another kind of element where F and X are not related linearly, let's say a bungee cord, you might have a nonlinear function that relates force and displacement. And it turns out that when you can make those kinds of linear approximations for components, you get linear equations for that system rather than nonlinear equations if, say, you can't make those kinds of assumptions. And when you do have linear systems, certain simplifying solutions can be made. And you'll learn all about that in 344. In 144L, we tend to cover these kinds of topics on a case-by-case basis, and you learn how to apply them and experiment with them in the lab. And you'll see in the lab that solving nonlinear equations, it can be much easier than solving a set of nonlinear equations where for many times we have to resort to a computer, and a lot of times with nonlinear systems there are other complexities. For example, how a system responds may depend on an initial condition, whereas in a linear system the form of the response may not. So there's a lot of differences between the two cases, and of course the linear case is always considered easier to solve and easier to deal with. So one of the things that we also like to and have an opportunity to do rather in 144L is we can study constitutive behavior of components of system models, and that's what we'd like to do in the lab, show you examples of how easy or difficult it might be to do that. So for the reason this is important is that in an application problem or a homework problem in 344, you might be given the relationship for a spring as just some stiffness K times X, whereas in the lab we may need to find those parameters, and so we'll spend quite a bit of time in the lab either showing how you can determine those stiffnesses experimentally, say, or how they might even relate to some of the formulas that you might have studied in related courses. So for example, in a machine design course, you might have found that you could estimate the stiffness of a spring, a coil spring, say, by knowing some of the fundamental design parameters. So you could see then, if you can understand how a system responds when the stiffness is changing, you can then you can then understand how, by changing key design parameters in the system, you could influence how a system responds and how its the overall system will behave given different types of inputs, say. So understanding constitutive behavior is a key part of this course, and so we'll do that throughout for each of the experiments, say, that we might study. A little bit of language here. Verification and validation are words that are used often to talk about models. In a modeling process, we often have to make decisions about a system, and the hard thing about a lab sometimes is that you're not just building the model, but you're trying to see if it fits the assumptions that you've made, and you make measurements to see whether the model is any good. We're going to say that we verified the model when we build the model, and it sort of gives us answers that we expect to see, right? Whereas when we say we validate a model, it means that we've actually compared the results from using that model to physical tests. So a validated model obviously has a higher standard than a verified model. They're both useful in different ways. And in this lab, we're going to practice both of these. The general approach in this course, as I've mentioned, is we introduce concepts that are related to your 344 Dynamic Systems and Controls course, but we will follow that learning those topics independently. We design lab experiments that can be challenging, but also we need to allow completion within a limited lab time, so generally they're simple experiments, but also practical. It also requires that you prepare before lab using the pre-lab exercises. Some knowledge in circuits and electronics is essential, not so much because those are dominating the kinds of experiments you're going to run, but because they're always present in the sensing and instrumentation that you use, and so it's helpful to feel comfortable with this subject matter. Experimentation is a key part of engineering, so we like to sometimes give you the opportunity to build skill and confidence in working in the lab and knowing what do I do next, right? What experimental labs, what kind of labs should I run to answer particular kinds of questions? So the TAs will often challenge you to do that on your own and not necessarily give you all the steps that are required to complete experiments. That is part of what we're asking you to do in this course. We also emphasize the use of computers for instrumentation control, for simulation, as I've mentioned, and also as part of control loops. So when we introduce feedback control, we'll actually be using computer-based control. And finally, there's a lot of different types of software that you need to know as an engineer. In previous courses, you might have learned to use MATLAB for analysis, for example. In this course, we choose to introduce and emphasize the use of LabVIEW as a new tool in case you haven't used it, and it tends to be a very useful tool for use in application, and not only in future academic work, but also in industry. It's a heavily used software environment as well. To give you an idea of the types of labs, let me just review very quickly. We have, to give you an idea of the simple types of experiments that we have, the questions aren't always easy. So we might study a pendulum, which is something that you've studied for in many different ways, in many different courses. The nice thing about a pendulum experiment is that you can study dynamics and the viability of different models that you could build using Newton's law, say. But we also have nonlinearities in here due to the motion of the pendulum, but also because of friction, say, in this pivot. So we will review development of mathematical models, say, in this form. I'll let you review that on your own. Applying Newton's law and understanding, well, how does nonlinearity arise because of motion? And you can see this sine function here is a form of a nonlinearity due to the angular motion of the pendulum. So these are some of the basic ways that we introduce some of these important topics that you'll see in 344 as well. Another experiment that is very relevant to practical applications is filling of vessels. So we do a single and two can experiments. There's inherent nonlinearity in the flow through this orifice, and you'll study that. You'll try to parameterize how the flow is governed by pressure drop, and you'll apply basic principles from fluid mechanics, say, that you studied in that course. But we will look at this type of system through the lens of a dynamic systems perspective. Instrumentation is introduced through simple beam experiments. So this allows us not only to study beam dynamics, but also instrumentation for measuring, say, motion using what's called an LVDT to measure the tip displacement of this beam here. And we also introduce strain gauge instrumentation. So you can see in this way we're introducing not only, say, the dynamics of the beam and how we can model that, but also how we use strain gauges to measure, say, the force or displacement of this beam. And it introduces you to the use of strain gauges as in an instrumentation context. Finally, we've also introduced another dynamic vibrational experiment that's a two-story system as an application and a way for us to use accelerometers to measure motion. So this two-story system is fixed here at the bottom, and these two stages vibrate laterally. These spring elements here represent, for example, the lateral stiffness of, let's say, a building vibrating. And this gives us an opportunity to study sort of a higher order dynamic system and the ability for us to use some more advanced methods for modeling and predicting some of the say, natural frequencies of motion for the motion of this type of system. Again, these are topics that you're going to be introduced to in your ME 344 class, and you'll be able to see them in a practical context in this course. Finally, in our controls experiment, we kind of step into that by introducing measurement using vision. We use vision to measure the motion of this needle on this little analog meter, which is a simple way to measure voltage, but we use this as a dynamic system. We introduce you to this electromechanical system and modeling of the electromechanical systems, use of a webcam to measure the motion of this needle, and then we show how you can put that system within a feedback control loop to try to measure and also control the position of that needle, and in that way introduce you to building a feedback control system and concepts from basic feedback control. Many colleagues that you'll meet in the future will be students maybe that have been in other programs, and you might meet someone who's had a whole course in measurement systems. Here in the mechanical engineering program, we introduce measurement systems through the different course applications. So you might have had measurement concepts introduced in heat transfer, in fluids, and now in dynamic systems. Challenging part of measurement is that you're putting together concepts from sensing, from electrical, electronics. You're doing some modeling to understand how those systems behave, understand concepts from signal theory. So this is a challenging part of measurement systems and measurement science, if you like. So keep that in mind, that what we're trying to do in this course, in addition to teaching you about dynamic systems and how to experiment with them, is trying to give you also some of the fundamentals that you might need to know with regard to the use and application of measurement systems concepts. And so we try to give you as much as we can to supplement what you've learned in other courses that have also tried to do this in our program. We use computer-based methods for instrumentation and analysis and control in this course. We make use of LabVIEW for that. We will show you how to develop systems, which means the integrated computer, sensing, and instruments and so on, to manage how data acquisition hardware is used to collect signals, say, from sensors, how to process data, display results. And also we use the same environment to show you how you can solve differential equations then of system models that we've developed for different laboratory experiments. Part of what we'll do is compare model results to experimental results, again, using computer-based methods. Finally, as I mentioned, we will show you how to implement feedback control systems using LabVIEW. And in summary, the course, I emphasize, you'll be introduced to concepts from from your DSC course maybe in a different way, and primarily focus on applications to the different laboratory experiments that we handle. We emphasize hands-on skill development. For that purpose, we have the hands-on quiz at the end, and as you saw, the experiments are relatively simple, but hopefully they're useful in demonstrating some advanced concepts and introducing sensing, instrumentation, modeling and simulation, and so on. So in the first few weeks of this lab course, we will be introducing the LabVIEW software and its usage, and you'll see that in a related first lab.